Hi, come back. We have already done the equation for the energy. The energy is given by 3 by 2 and kT Fy by 2 z over F3 by 2 z, where we know Fy by 2 z and F3 by 2 z are the Fermi Dirac functions. Okay, and it is given by this expression. It can be represented as an integral, or it can be expressed as a series. Okay, a series in terms of z. Now that is our mean energy or energy of the system, and we had this relation pressure equal to 2 by 3rd of the energy density, which is a standard result. Now we are going to calculate the specific heat CV of the gas that is obtained by CV equal to dou U by dou T, where number of particles and volume is constant. So here I am going to use for U 3 by 2 nKT Fy by 2 z over F3 by 2 z. So that is used here for the energy 3 by 2 nKT Fy by 2 z over F3 by 2 z. So dou U by dou T means we have to differentiate this thing with respect to temperature, and what we are keeping constant here is number of particles and volume. So as we differentiate with respect to temperature, remember that here we have temperature and Z also contains temperature. Z is exponential of mu T, mu temperature. So this also contains temperature. So there are 3 terms containing temperature. So keeping that in mind, we apply the product rule. So first we differentiate with respect to temperature, and we get 3 by 2 nK Fy by 2 z over F3 by 2 z. Then we have the 3 by 2 nKT F3 by 2 z, and we are differentiating Fy by 2 z with the temperature. Then we have 3 by 2 nKT Fy by 2 z, and differentiating this 1 by F3 by 2 z with respect to temperature. So the thing is, we are applying the product rule, and there are 3 terms containing temperature. CV dou U by dou T. CV is dou U by dou T for number of particles and volume fixed, and it is obtained by this expression. So here we have to take dou by dou T of Fy by 2 z. Okay, dou by dou T of Fy by 2 z, and here dou by dou T of 1 by F3 by 2 z. So this is a function of z, where z is a function of temperature. So I am writing this as dou Fy by 2 z dou z into dou z by dou T. Here what I do is I write this as dou by dou z of 1 by F3 by 2 z. Okay, dou by dou z of 1 by F3 by 2 z into dou z by dou T. Okay, so this is when I differentiate with respect to z, I will get minus 1 F3 by 2 z to the power minus 2 into F3 by 2 z by dou z. This is dou z, not dou T. Dou z into dou z by dou T. Okay, so this is what we get here, and we use 2 results. One is this dou by dou z of F nu of z, that is 1 by z F nu minus 1 z. We are using this result. This is a standard result for the Fermi Dirac function. We are using this without the proof. Another thing is 1 by z dou z by dou T, when volume and number of particles fixed, is minus 3 by 2T F3 by 2 z over F half of z. Its proof is given here. We have a dou by dou T of F3 by 2 z. that is dou by dou z of f3 by dou z into dou z by dou t. Okay, this is written in this form, and this one is 1 by z f half of z dou z by dou t. This thing we can differentiate with the temperature. Okay, this thing I differentiate with the temperature, lambda is there. So we will get this, okay, by introducing a T here, temperature here, I can get this. From this dou z by dou t, we can get as minus 3 by 2t z f3 by 2 of z by f half of z. So these two results, okay, dou by dou z of nu of z, 1 by z dou z by dou t. These two results are applied here. Here we have dou by dou z of f5 by 2 of z, that is 1 by z f3 by 2 of z. Okay, and dou z by dou t, from this dou z by dou t is z into minus 3 by 2t f3 by 2 of z by f half of z. Okay, so that is written here. The same thing is done here also. Here f3 by 2 z by dou z, that will be, okay, 1 by z f half of z. Okay, dou by dou f3 by 2 z by dou z. This is not t, this is z. So that will be z f half z, and dou z by dou t, as we did here, we substitute this. So the third term will be this. This will be the third term, and we simplify this and we get this expression. Okay, the three terms are this, and these two terms combine. We have f5 by 2 of z by f3 by 2 z here. Okay, f5 by 2 z by f3 by 2 z. Several terms here cancel. So the final result will be this: Cv equal to Nk 15 by 4 f5 by 2 z. So this is the result. Okay, so Cv by Nk will be 15 by 4 this f5 by 2 z f3 by 2 z minus 9 by 4 f half of z by, sorry, f3 by 2 z by f half of z. So this is Cv by Nk. So we did all these things for finding Cv. The Helmholtz free energy, we are now going to determine. It is A equal to G minus PV. G is the Gibbs free energy. We know G is mu n, chemical potential into number of particles. So this is n, mu is kT log z. kT log z we know from the definition of mu, or further from the definition of Z. The fugacity is Z equal to e to the power mu by kT. So that is mu is kT log z. PV is 2/3 of energy. Okay, PV is 2/3 of energy. We know pressure is 2/3 of energy density. So PV is 2/3 of energy. So n kT log z and minus, this is 2/3 of energy. We know U is equal to this. U is equal to 3 by 2 n kT f5 by 2 z by f3 by 2 z. Okay, we know U is this. So our U by n, sorry, 2 by 3 U will be this nkt f5 by 2 z by f3 by 2 z. So when I take nkt as common factor, this will be log z minus f5 by 2 z by f3 by 2 z. So another thermodynamic quantity is determined, which is the Helmholtz free energy. Now another one is entropy. Entropy is this: U minus A by T. U equal to A plus Ts. We know S equal to U minus A by T. U is what? 3 by 2 and kT f5 by 2 of z by f3 by 2 of z. And A is, we just determined, this is A, and kT log z minus f5 by 2 of z by f3 by 2 of z, that we substitute here. Okay, so temperature gets cancelled. So what we get when we combine these two, 3 by 2 Nk and plus Nk, okay, minus plus Nk, f5 by 2 z by f3 by 2 z. When they combine, we have F5 by 2 nk F5 by 2 of z by F3 by 2 z, then minus nk log z. I'm taking nk as common factor, so I have 5 by 2 F5 by 2 z F3 by 2 z minus log z. So we have determined several thermodynamic quantities. The energy, okay, we first determine the energy. This is the energy, and then we determine the pressure. This is the pressure. Then we determine the specific heat capacity at constant volume. Thereafter, we determine the Helmholtz free energy. This is Helmholtz free energy. A is the Helmholtz free energy. Its expression is this, and then we finally determine the entropy. Okay, so for an ideal Fermi gas, starting from the first two equations, we determine several quantities by using this function, Fermi Dirac function. Now we are considering few cases. One is classical case, which is called a non-degenerate case. Okay, non-degenerate or classical case. If the density of the gas is very low, I'm writing this equation F3 by 2 Z equal to n lambda q by g. So where did I get that? That is obtained from the equation 4. See, equation 4. Equation 4 is this. This n by v, capital N by v, that is written as small n, the particle density. This is written as particle density. Okay, so F3 by 2 of Z will be n small n lambda cube by g. This is particle density small n lambda cube by g. That will be F3 by 2 of Z. So that is written here. Okay. For the classical case, we are considering the classical case, which is also called non-degenerate case. F3 by 2 Z n lambda cube by g. Suppose that the density of the gas is very small. This is very small, and the temperature is large. Okay, and or temperature is very large. Lambda has temperature in the denominator, so temperature large. Then this will be very small quantity. Okay, this will be far less than. So F3 by 2 of Z will be far less than 1. Okay. So in that case, we can say F3 by 2 Z is equal to Z. Okay, F3 by 2 Z is very small, and it can be written in terms of Z. F3 by 2 Z is very small. You can approximate it by Z. Okay, so this is Z is very small. F3 by 2 Z small, Z very small. Okay, Z is very small. So we can generally write F nu Z equal to Z. Okay, from this expression, F3 by 2 Z is very small. If the density and temperature, density is very low and temperature very high. So F3 by 2 Z is very small. So this can be written in a series. Z minus Z square by 2 to the power 3 by 2 plus Z cube by 3 to the power 3 by 2, like that. So F3 by 2 Z is very small, so it can be approximated by Z. Okay, and so Z will be very small, and if Z is very small, much less than 1, okay, much less than 1, then this F nu of Z, generally F nu of Z, which is written by this series, that will be equal to Z. Okay, so in that case, F5 by 2 of Z will be equal to Z, F3 by 2 of Z will be equal to Z, F half of Z will be equal to Z, because F nu of Z is Z. So pressure, we know it is 2 by 3rd of U by V. U is this 3 by 2 nkt F5 by 2 of Z by F3 by 2 of Z by volume. This is Z if Z is very small, or F3 by 2 Z is very small. So this is Z, this is Z. That get cancelled, so we get PV equal to nkt. Okay, and U is 3 by 2 nkt. How do we get U equal to 3 by 2 nkt? U we know 3 by 2 nkt F5 by 2 Z by F3 by 2 Z. This is approximated by Z, so U equal to 3 by 10 kT, and CV is 3 by 2 Nk. And what about Helmholtz free energy? That is equal to Nkt log Z minus F5 by 2 Z by F3 by 2 Z. Okay, and this is equal to 1. This quantity will be equal to 1 because this is Z, this is also Z. So Nkt in bracket log Z minus 1. Now we are writing F3 by 2 Z is Z. Z very small, so F3 by 2 very small. So that is equal to Z. So that is equal to N lambda Q by G. So log Z is log N lambda Q by G. So the Helmholtz free energy is Nkt log N lambda Q by G minus 1. And what about the entropy? This is the expression for entropy. Okay, S equal to Nk 5 by 2 F5 by 2 Z F3 by 2 Z minus log Z. Again, this thing is 1. F5 by 2 Z is Z, F3 by 2 Z is Z. So this is 1. So 5 by 2. This is log N lambda cube by G. So this is the entropy. Now, if the parameter Z is small in comparison with the unity, but not very small. Here we assume the Z is very, very small. F3 by 2 Z is far, far less than 1. Very, very small. And this is very, very small. When Z is very small, F3 by 2 Z will be very small, and F3 by 2 far, far less than 1, then Z will be far, far less than 1. Okay, but suppose that Z is small in comparison with unity, but not very small. Okay, then using this equation, we write N by V, the particle density, as equal to this G by lambda cube. This is the series expansion for F3 by 2 Z. Okay, so I am writing Z minus Z square by 2 to the power 3 by 2, Z cube by 3 to the power 3 by 2 equal to lambda cube by Vg. We know what is this small v. This is the specific volume, that is inverse of the particle density. So this is the series. Then what we do, we invert the series. That is, we write Z in a series form of lambda cube over Gv. Okay, we invert the series. So what will be PV by Nkt? Okay, PV by Nkt we know. That is, what is PV by Nkt? PV by Nkt will be Gv by N lambda cube G5 by 2 Z. Okay, G N PV. Okay, as Gv N lambda cube, or G or lambda cube V by G. You can write this as 1 by lambda cube V by G. Okay, F5 by 2 Z. So here this F5 by 2 Z, that is a series in terms of Z. Now from this we have got Z in terms of lambda cube lambda cube V by G. So we are expressing this Z in the F5 by 2 Z in terms of lambda cube small v by G. We are expressing. So we get this. So we are getting this PV by Nkt in terms of lambda cube V by G. Okay, and since the PV by Nkt has a term lambda cube Vg in the denominator, as we divide, we will get this Al lambda cube by Vg to the power L minus 1. Okay, this power will be L minus 1. This is L, but as you divide it by the lambda cube by Gv that is present in the denominator, its power becomes L minus 1. The same thing we have done in the Bose gas as well. So this is our PV by Nkt, and this is the equation of state of the gas. Okay, equation of state for the ideal Fermi gas. And here we have minus 1 to the power L minus 1. Okay, the first term is positive. When L is 1, this first term will be positive. Next term will be negative. Okay. So Cv, so this is the equation of state. So we have obtained the equation of state of the ideal Fermi gas when Z is less than 1. Okay. If it is far less than 1, okay, Z is far less than 1, the equation of state will be PV equal to NKT. So what is Cv? Cv is dou U by dou T, that is dou by dou T of U is 3 by 2 PV. You know, U is 3 by 2 PV. So for PV I am substituting this. I get PV from this. So this is 3 by 2 NKT, sigma L equal to 1 to infinity this. Okay, and we are differentiating this with respect to temperature. Remember that we have temperature here. Here also we have temperature. So we have to apply the product rule. Okay, so we get this. So this is 3 by 2 NK. This time 5 minus 3L by 2 AL. So as we, you know, these are all AL are the coefficients. These are called viral coefficients. We have seen in the ideal Bose gas. They have some definite value. Okay, these coefficients, these are viral coefficients. So in terms of those viral coefficients, if you expand this, you get this result. So Cv is equal to 3 by 2 NK into this series in terms of lambda cube by GV. Now at a finite temperature, okay, and the temperature is very large, temperature is infinite, all these terms will be 0. So Cv will be 3 by 2 NK. But at a finite temperature, the specific heat of the gas is smaller. It will be smaller because of the presence of this series. For a finite temperature, for a finite value of the lambda, the Cv will be, specific heat will be less than this value, 3 by 2 NK. Okay, so this is what we see for the specific heat.